Hello, I'm Brian Dower, and I'm here with Hernan Avalos in Group 8. We are discussing the research paper Tarsal, Reconciling Scheduling Speed and Quality in Large Shared Clusters.
Okay, so I will be discussing the first motivation slide, and that's the problems with clusters. So to begin, large-scale data centers struggle hosting multiple different applications while maintaining efficiency and can make scheduling difficult. So, yeah, so there's just varying source demands, CPU heavy, memory intensive, also latency issues. Um, Following this, based on the paper, it described that schedulers should have three properties. The first one being that each workload should receive resources that enable predictable high performance. So that's critical for latency sensitive workloads and any actions that are interactive like queries. Um, Following this, jobs should be tightly packed enough to achieve a high cluster utilization. That basically says that you want to make sure that utilization is properly held because if you waste any resources, that can get expensive for anyone working on the cloud. And cloud providers always want to maximize their return on investment, especially when they invested heavily on hardware. Um, there's also something called when people are overly cautious whenever scheduling and they're more on the conservative side, it would lead to like underutilization. So not using enough resources allocated. Following that, they also mentioned that scheduling overheads preferably should be kept minimal to allow schedulers to scale to large clusters and high job arrival rates. Um, yes, so uh, and as seen above, this is an important practical problem for data centers and cloud computing environments where many tasks should be performed simultaneously.
Um, so with centralized scheduling, such as Quasar and sample-based scheduling, such as Sparrow, these are two scheduling algorithms that can be employed to solve our problem of hosting multiple different applications while maintaining efficiency. So with these two methods, they will greatly impact the data center and use more resources and schedule tasks more responsibly. Uh, However, there are some major drawbacks depending on which scheduling implementation you use. So some issues with centralized scheduling is that it includes having a high latency with overheads. There's this scalability bottleneck due to single decision making entity limiting throughput. There's poor responsiveness due to high workloads, and there'll be delays. The delays will affect the quality of service guarantees in resource allocation. For sample-based scheduling, there's low latency and high throughput decision. It will ignore resource heterogeneity, which will negatively impact the performance and resource allocation. It will also struggle with performance predictability when it comes time to process high loads.
Yep. And the next slide, we'll be discussing the visualization of scheduling. This is the first part. So distribution of job performance comparing Tarsal to sample-based and centralized scheduling for short, medium, and long duration tasks on a 200 server cluster. So that is the three figures on the left. A short represents the Spark task that should take around 100 milliseconds. Medium or Spark tasks that take around 1 to 10 seconds. And the long is head loop tasks that take 10 seconds to 10 minutes. Ideal performance or operating at 100% usually assumes that no scheduling overheads and no degradation due to interference. And the cluster utilization is 80%. So just to add on to this, figure 1A is sampling-based scheduling. That's more similar to Sparrow-like. As you can see, based on the first figure 1A, low scheduling latency. Short jobs, they perform relatively well, and most of those jobs are in the 80 to 95% range. A plus for that is that low scheduling latency, it will help meet execution deadlines, meaning that it will run pretty fast. However, on the downside, medium and long jobs, they suffer in figure 1A. And this will result in significant performance degradation. So a lot of these jobs fall below the ideal 50%, likely due to the lack of awareness of their preferences within the hardware. Following this, looking at figure 1B, this is the centralized scheduling, which is more Quasar-like. Here, long jobs will benefit the most, and they'll likely be concentrated near the 95 to 100% range. So with this, on the other hand, they are sophisticated and more decision-based, logic-based reasoning, and it is a full state visibility. So this is more ideal for resource-aware batch jobs like Hadoop. Sorry, and here short and medium jobs will do worse compared to long jobs. And finally, on figure 1C, this represents Tarsa, which is a combination of the two or a hybrid. Performance is consistently high across all durations. That includes short, medium, and long. Tight clustering is usually around 90 to 100% for all three, short, medium, and long jobs. And very few jobs will fall below the 80% mark, even if it's under load or heavy load. So some of the plus is the speed of sampling, the quality awareness, and the smart admission control. Okay, next slide.
Right. So just the impact of poor scheduling. So sampling-based schedulers are sensitive to the poor selection of resources. They're more focused on speed and ignores the critical performance resources, degrading the performance, as discussed in the last slide. And centralized schedulers, they try to find the highest quality placement and are penalized by scheduling overhead, creating delays. And as we saw, Tarsal is the best case where we can schedule short, long, and medium tasks closest to the ideal performance while finding the highest quality places. Yeah.
Okay, and I'll be discussing the goals for Tarso. So to begin, the purpose of the shared state Tarso is to combine the speed of sampling-based systems with the high quality placement and intellectual property of centralized schedulers. So this basically would like to fuse the speed and throughput of sample-based scheduling with the quality aware, conscious decision-making of centralized schedulers. Following this, it allows for decision-making to be interference aware, heterogeneity, conscious, and scalable. So it basically means that they want to select the appropriate hardware and the appropriate profile to maximize efficiency. And scalability often means that since there are multiple agents, they would like to or prefer for them to run in parallel without something coordinating or having to tell it exactly what it has to do at all times. Following this is resource selection. It should directly reflect the performance sensitivity to hardware and interference. And finally, it'll introduce analytically derived sampling and admission control in order to create a path to select resources with the highest degree of guarantee possible. Um, Oftentimes and later on discussed, there will be admission control holds, jobs, back when good resources are unlikely to be found, rather than wasting resources or placing poor scheduling decision makers, I guess. Yep, you can go to the next slide.
So the promise for Tarsal. So as we will see, with Tarsal, there are certain promises it makes when implemented in a cloud computing environment. So it will reduce the performance lag and it improves the predictability of applications. It achieves low latency, high quality scheduling, and the ability to scale effectively into multiple large heterogeneous clusters under diverse workloads. The solution combines the best of both sample-based and scheduling, sample-based scheduling and centralized scheduling. It is incremental yet meaningful advancement because it builds off Sparrow, which is more like a fast and dumb scheduler, and Quasar, which is like a smart but a slow decision-like scheduler. So it is not really a new architecture, but refines the existing techniques to perform well in a heterogeneous high-load environment.
And with the job cycle within Tarsal, to begin, it'll start with a profile lookup. It'll find a job's preference and their interface sensibility. Platform preferences basically mean that what is the proper architecture for the server to run on, and interface interference sensitivity, sorry, is how susceptible the job is to share resource contention. And these characteristics inform later decision making during sampling and placement. Following this, the next cycle would be admission control. This decides whether or not the cluster will likely yield a resource that is suitable. And if incompatible, it will defer. So whenever there may be high cluster loads, the admission control may be unlikely to find high quality resource quickly. So rather than waste CPU cycles on poor matches, Tarsal queues based on estimated waiting times. Next is adaptive sampling. This will select resources by using a sample size, or R, to try and meet a TW, or target quality. So this is statistically based. Oftentimes, a larger sample size will increase the chances of a good match, but will also add latency and any risk for conflicts. So this is important in a core innovation due to the fact that it will be using statistics to possibly guide a faster decision making to high quality sampling. And finally, allocation and monitoring. It performs monitoring real-time performance, assigns resources, and creates connections when needed. Sorry, corrections when needed. You can go to the next one.
So the designer main idea for the interference and aware profiling. So right. So Tarsal models interference sensitivity using the 10-dimensional vector to detail any job pressure on the shared resources. So The closer the resource is to the beginning of the rate equation, the more resource intensive the task is. So C1 will be like more resource intensive than C3. Below is a vector encoded with the order sustained scheme. So in the order sustained scheme, the closer the weight of the equation is to 1, the more resource intensive the job is, and that it demands more resources, meaning that it will need to be scheduled to the resource unit that wisely, and that its performance will depend on the scheduling decision.
And for resource unit or RU, Tarso manages the resource at RU granularity using Linux containers. RU enables exceptional or superior decisions, as well as supporting interference tracking for every job. Resource units consist of one physical core, an IC bandwidth, partition memory and storage. And a direct example is a 16-core server with 64 gigabytes of RAM, yielding 16 RUs or resource units. Each of the resource units will have 4 gigabytes of memory and 625 megabytes per second network capacity. So you may ask, like, why Linux containers? Containers will provide strong isolation between the RUs for CPU memory and input-output bandwidth. When compared to virtual machines, containers can be more lightweight and enable faster tasks with lower overhead.
So sample size versus cluster load. When cluster loads increase, there is less high quality resources available. So Tarsal will increase its sample size in order to maintain a high chance of selecting the proper resource unit. Statistically looking at this, we see that the resource cumulative distribution function on D, which is the uniform distribution of quality after sampling. As the cluster utilization increases, the number of high quality or most compatible resources units drop. So in order for the best performance, the closer utilization rises and gets closer to 1, which is the ideal performance. So Tarsal must adapt the sample size to the closest curve on TW. And in this case, the target job quality threshold is 0.92, which is pretty optimal. Yeah, so as you see in the graph here, we saw that at D equals 0.92, at R equals 32, so R must be greater than or equal to 82 to push below 10 to the negative third.
So this slide will discuss the need for admission control. We have 3 problems here labeled. The first one being when cluster load is high, good quality RUs are hard to find. So the resource units. So oftentimes when clusters fill up, most of the top quality resource units will already be occupied. This increases the difficulty of satisfying demand workloads, which are oftentimes those with high target qualities. Following this, larger sampling sizes are needed to meet quality guarantees, but as a result may cause an increase in latency. So Tarso uses probabilistic guarantees to match job preferences to resource quality. And finally, naive RU availability checks are not enough anymore. So this will mean that raw RU count will not be sufficient enough to evaluate resource quality. Um, so like it says, you can't simply count available RUs. Oftentimes it won't account for the profile, for interference, or any characteristics in regards to hardware. A solution. The first one is that Tarsil passes down scheduling decisions when top quality RUs are not around. And this is done by using the lightweight admission control mechanism built within. So oftentimes when, let's see, also when a job arrives, Tarsil doesn't immediately attempt the scheduling. And if there are no compatible RUs, it's that are likely to be found, it'll defer the scheduling job and it'll be placed in a queue in order to avoid any time wasted.
So the need for admission control. So in our activity schedule algorithm shown on the graph to the right, there's an X in already allocated resource units. The Stripe resource units are sample candidates for a task. In this case, R equals 4 for a task. The solid black resource units, such as RUA and RUB, in the top right scheduler picture, are the selected units to the new job. So after this marking or sampling is done, the scheduler will then assign the best quality resource units, or the resource units that are marked in black, considering the job's structure and preferences for resources. There's also awareness sampling, when admission control will take into account performance benefits for tasks that need cache sharing, data locality, or inter-task communication overhead in assigning resources to certain jobs.
In regards to final implementation, the best way to explain it will be using these two figures, figure 7 and figure 8. Figure 7 has no central coordinator, and that means that it will run decentralized. Each scheduling holds their local cluster state copies as well. And they will all have the ability to sync and has an atomic commit to the master cluster. And local monitors constantly update RU status and triggers auto scaling. Just to discuss the component, well, the purpose of figure 7 to begin is that the diagram, it'll illustrate exactly how Tarsil is distributed as a shared state scheduling system, showing how scheduling agents interact locally and with the global state, working servers and monitors. So a breakdown of the components. You'll have on the top left the admission control, and that's the first line of defense under high cluster loads. Following that, you'll have scheduling agents, which run in parallel with local copies of the cluster state. This allows scheduling decisions to be made independently and synchronize state periodically with the master cluster state. You also have worker servers. Each has a local monitor responsible for updating the RU usage, reporting job performance metrics, detecting resource saturation, and it supports auto scaling and job migration. Following this, you have something we're familiar with, which is the resource units. This is a subdivision of a physical server, which then isolates slices using the Linux containers. Granular units of scheduling includes like we mentioned, the one core proportional memory, disk, and network. And finally, on the far right, you'll have your master cluster state. It'll serve as the global truth of RU status. This is usually only updated via atomic transactions by scheduler agents. Yeah, a couple key interactions within it. Green arrows represent informational updates and syncs, while black arrows will control the flow, including launch tasks and admission decisions. And the red arrow is the atomic commit attempt to master state. Following that, we have figure 8. The purpose of this figure is to provide a time-based trace of how a single job can flow through the Tarcell scheduling system. So that's basically from submission to completion. I will give a sequence breakdown real quick. This will be from top to bottom. First, it'll start with job submission, which begins at the cluster front end with submit.log. And this is routed to admission control, which will decide to queue or to dispatch it. Following that, scheduling agents will run 3 key methods. The first is sample RU, which will select a candidate RU based on the sample size. Following that, they'll compute Q, which will evaluate the quality for this job. And finally, the select RU will choose whichever is the best match. Third is the master state copy, and this is where agents attempt atomic write to commit allocation. If it's successful, acknowledgement will be returned, and if not, it'll resample and retry. There is also local monitor and worker agent calls. This will first is allocate RU. This will reserve the resource, and launch task, which executes the job. Monitor job performance, and it will trigger corrective action if deviation occurs. And finally, you have the final step, which is completion. If a task completes, you'll see completed task called. Local monitor will update RU availability, send updates to master slates, and it'll have an admission control. And also a couple key information is that figure 8 contains fast scheduling, anywhere from 10 to 20 milliseconds. It has feedback loop after a task is completed. RU updates push change towards an admission control, and resampling and incremental writing can thwart any conflicts. Next slide.
So for our evaluation, in evaluating Tarcell, so there's main results for some key areas. We found that there were some features of Tarcell that make it very enticing to implement in cloud development. So the sampling size is typically 8, which is good for high and low cluster loads and provides high quality scheduling decisions. The number of scheduling agents is decreased in Tarcell when compared to Sparrow, which needs 10 agents to get a fair comparison to Tarcell. The decreased number of scheduling agents reduces overhead and complexity when fulfilling the needs for complex workloads. In cluster loads, with smarter sampling and admission control, the average response time will be constant for Tarcell until loads are over 85%. In task duration, the response times will be low, ranging anywhere from 10 milliseconds to 600 milliseconds for average and 95th percentile tasks. And Tarcell also features priority-based task execution, where the response time is reduced for any task with priorities.
And for comparison of methodologies, we compared the performance of tasks in Tarcell with methodologies such as Sparrow and Quasar. On an overall comparison of across 7,200 jobs assigned on multiple EC2 servers, Tarcell has the most ideal performance compared to sampling-based and centralized scheduling. Down below, you can see there's a visual interpretation of a performance curve chart. On the x-axis, you'll see the workload index, which will scale from 0 to 7,200 jobs, and it will order the jobs by performance from worst to best. On the y-axis, it has the speed up normalized to ideal, and this will measure how close the job execution time is to the optimal, sorry. And this is with no overhead and with perfect placement. The lines, black will symbolize ideal performance. This is the theoretical upper bound, and it's perfect scheduling with no delay or interference. The purple, or the distributed sampling, represents Sparrow style sampling, which is the wide variance, and many jobs far below optimal due to interference and lack of preference awareness. Green is the centralized greedy, or the Quasar style global optimization. Better than sampling for for some tasks, but it'll incur high scheduling latency. And this is especially visible in the tail. Red represents Tarso, which is the closest to ideal, constantly achieving 90 to 100% optimal performance across most jobs, even under the high load. Let's see. Next, slide.
So for the Tarsal performance comparison, so seeing the graphs to the right, Tarsal was compared to sample-based and centralized scheduling in the batch with 7,200 jobs. The graph to the top right shows a significant decrease in scheduling time with decreased overhead. Centralized timing caused a 1-second addition compared to Tarsal that only added 150 milliseconds onto workloads. So if you see the graph to the right, the red line shows the centralized scheduling time, and versus the Tarsal, which is almost like opposite. So, and the green is the sampling for Tarsal, where the blue is the queuing time. So definitely a huge increase there. We're of centralized versus Tarsal with the overhead timing. The sample-based and sample-based scheduling to the graph on the lower right of the slide, we are comparing on the left graph sample-based scheduling to the graph on the right, which is Tarsal scheduling. So if the graph shows more region of darker blue towards the bottom of the graph, then the resource quality is worse off. The quality of cores for sample-based scheduling was less than 0.4 at times when Tarsal only had 18% of cores less than 0.9. In conclusion, for the evaluation, Tarsal is able to complete 4 times as many jobs than sample-based scheduling and 2 times as many jobs in centralized scheduling.
And then finally, our conclusions found that first, Tarso is a superior methodology compared to sample-based and centralized scheduling methodologies, which the authors display. We believe that they achieved what they set out to do, which was explained why Tarso was a better scheduling method than current solutions such as Sparrow or Quasar. However, the authors did not address any drawbacks, or not that many drawbacks, with Tarso, which should have been discussed when considering for cloud computing job scheduling. I also noticed that it's more so focused on a specific cloud computing scheduler and not really tested across different platforms as well. So Tarsal also has drawbacks in modern day scheduling, with jobs such as machine learning. Um, Kubernetes has more real world applications compared to Tarso. Also, considering that the paper is 10 years old, there have probably been more recent developments within this problem area that need to be investigated further. Yep. So we would like to thank you for listening in to our presentation. We hope you learned a couple things about Tarcell. We enjoyed learning and reading this article, especially creating this slideshow for you to watch. And yeah, you have any input, Ryan?
Yeah. You have any questions, put it in the comments below. But it was very interesting reading this paper and learning about Tarsal with respect to just scheduling methodologies. It was very fascinating just to learn about the different methodologies and why Tarsal can sometimes be superior.
Yep. I think that was well put. And yeah, thank you for watching. Bye-bye.
Thank you.